Welcome to lecture night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. I'm happy to be your host for tonight's lecture. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss working from the DDO facility, we are happy to bring you the lecture nights we had planned for the summer through this webcast instead. It's my great pleasure to introduce our speaker for tonight's lecture, Emily Deibert. Emily Deibert is a PhD candidate and Vanier Scholar in the Department of Astronomy and Astrophysics at the University of Toronto. Her thesis focuses on observing exoplanet atmospheres with large ground-based telescopes around the world. Emily also works as a freelance science writer and likes to spend her free time reading. Tonight, Deibert will be talking about extraordinary exoplanets. If you, our viewers, have questions for Ms. Deibert, please ask them in the YouTube chat. She will have some time to answer questions at the end of her talk. Please join me in welcoming Emily Deibert.
Okay, thank you so much, Denise. And thank you to the RASC Toronto Centre and the DDO for inviting me. Before I start, I just want to say I'm sorry we can't be there in person. This was a photo I took last time I was at the DDO, and it's about 5 years ago now, so I was really looking forward to going there again, but I hope we'll be able to sometime soon. And please feel free to also tweet at me if you have questions that you think of after, or just want to connect after the talk. My Twitter handle is right there. So tonight I'm going to be talking about my research on exoplanets. And in terms of astronomy, I think exoplanets is kind of a younger field. So when I was born, we really only knew about 9 planets in our solar system. And we knew about a couple of exoplanets as well. So these are planets that orbit around other stars in our galaxy. And since that time, we've lost 1 planet. So sorry to anyone who's a fan of Pluto, but we've gained thousands of exoplanets. And to be specific, as of yesterday, when I looked this up, we'd gained 4,171 exoplanets. So this is how many planets we've discovered in other planetary systems in our galaxy. And what's really neat is that a lot of these planets are just totally unlike the planets that we have here in our own solar system. And so that's what I'm going to be talking about tonight. So how did we do this? How did we find all these exoplanets? So this is a graph showing the number of detected exoplanets every year since we first started detecting exoplanets, and it's color-coded by the different methods that we use to detect exoplanets. So as you can see here listed on the side, there are lots of different methods, lots of different ways to find exoplanets. But the main ones that I'm going to be talking about tonight are these 3. So the radial velocity method, the transit method, and the direct imaging method. So to start off, the radial velocity method, which is also sometimes known as the Doppler method or sometimes the wobble method. And this was kind of the first method that we really used to detect exoplanets. And the way this method works, or what it relies on, is the fact that, while you might think of planets as orbiting around stars, which are fixed in place, really the planet and the star are both orbiting around the common center of mass of the system. Because stars are so much bigger than the planets that are orbiting around them, this common center of mass happens to be really close to the star. So for the star, this orbiting is a bit more like a wobble, which is why sometimes you hear people call this the wobble method. So how do we use this to find exoplanets? So to use this method, we rely on something called the Doppler Effect. And a lot of you might be familiar with this because it is something that we experience in our day-to-day lives. And the most common example of the Doppler effect has to do with sound. So if you've ever heard an ambulance traveling by you on the street, you'll probably notice that the siren sounds, it has a higher frequency as the ambulance is moving towards you and a lower frequency as the ambulance is moving away from you. And you can kind of think of this as being because the sound waves, as you're kind of seeing in this diagram here, bunch up, we can say, as the ambulance is traveling towards you. And then they kind of spread out more in the direction that the ambulance is traveling away from. And so this causes the sound to have a higher frequency in the direction that the ambulance is traveling. So the same thing happens with light. A source of light, like we've shown here, a light bulb that's moving towards you, the light waves from that source will bunch up in the direction it's moving and shift to a higher frequency, which in terms of light means a bluer color. So we say that they're blue shifted. And on the other hand, when the light is moving away from you, those light waves kind of get spread out, as you can see here, and the light waves shift to a lower frequency, or a red shift. In this case, they become redder. And so that's really how this radial velocity method works. So like I said before, the star and the planet are both kind of orbiting around each other. And if you imagine that you have a system up like this, so that the star is moving away from us and towards us in our orbit, what we see happen is the light from the star gets bluer, as you can see in the bottom when the star is coming towards us, and it gets redder as the star is moving away from us. So that's because of the Doppler shift, right? As it moves towards us, these light waves get bunched up and bluer. As it moves away from us, these light waves kind of get more spread out and redder. And so that's how we use this method to detect exoplanets. We're not actually seeing, so this video here is a pretty big exaggeration. We can't actually see the star in most cases actually moving in its orbit like you see here. And we certainly can't see in most cases the exoplanet moving around. All that we're really seeing is the light from the star, and we're seeing this periodic change in color from the light. So if you're observing a star over time and you see the light periodically become redder and then become bluer, and it does this in a periodic pattern, then you can infer that there's probably an exoplanet orbiting around that star, causing it to wobble in its orbit like that and causing the light to be red-shifted and blue-shifted over time. So that's the radial velocity method. And like I said, that was kind of the first method we used to detect exoplanets, and it really kind of jump-started this field. So next is the transit method. And again, this is the plot I showed at the beginning, showing the different methods we use to detect exoplanets and how many planets each one has detected. And you can see here that it's overwhelmingly dominated by green, which in this case is the transit method, especially in the last couple of years. And in fact, out of those more than 4,000 planets that we've confirmed as of the past couple of days, 3,190 of them were discovered using the transit method. So that's about 3/4 of all the exoplanets that we know of that were discovered using this method, and many of them discovered, as you can see in the graph, the past couple of years since 2014 or so. A lot of those planets were discovered by the Kepler Space Telescope, which is shown here in a really nice artist's impression. So Kepler was operational for about 10 years. It ended its mission a couple years ago now. But during that time, it detected many of the exoplanets that we know of today through the transit method. Today, we have a similar telescope called TESS, which is doing the same thing, using the transit method to find new exoplanets. So what is the transit method? In the first method that I talked about, the radial velocity method, we're really measuring the changing color of light from a star to infer that a planet is present. With the transit method, what we're doing is measuring the changing brightness of light from a star to infer whether or not a planet is present. So if you imagine we have a similar setup here, we have a star with a planet orbiting around it, and the system is kind of edge on like this so that we can see the planet passing in front of the star. You can imagine that when we're just observing the star on its own with the planet maybe off to the side or behind it, we can measure some brightness for the star. And when the planet passes in front or transits in front of the star, it's going to block some of that light, because planets themselves don't give off a lot of their own light. Instead, it will block the light from the star. And so the overall brightness, the overall amount of light we're getting from the star is less. And so this is essentially what you see over time. As the planet passes in front of the star, it blocks out some of that light and creates a dip in the brightness that you can see on the bottom, and that's what we call a transit light curve. So if you observe a star for long enough and you notice these kind of dips in brightness happening periodically, then you can infer, just like we did with the first method, you can infer that a planet is there, and a planet is what's causing these dips in brightness. So on its own, that method sounds simple enough, but there are a few issues that make it more difficult than it might sound. So the first is that relative to the stars they orbit, planets are really small. In the example that I showed before, I showed a really large planet blocking out a lot of light, and in that the GIF that we saw previously, there was a big dip in brightness that was very obvious. But in reality, planets are much smaller than the stars they orbit. And in fact, even the largest planets that we are likely to detect are really a fraction of the size of the stars they're orbiting. And so in this case here, that might be a bit more realistic in terms of the size of the planet we might detect. That planet's not blocking a lot of the light, right? We're really not going to get a huge dip in brightness. So you really need sensitive instruments to be able to measure that dip in brightness. The second kind of main issue with this is that stars themselves are pretty messy. In the examples I showed before, we kind of assume the star has a constant brightness until a planet passes in front and blocks some of that light. And you see a very clear dip in brightness. But in reality, there's a lot going on with stars, right? This is a real video of our sun taken by the Solar Dynamics Observatory. And you can see there's a lot going on. There are these kind of brighter spots. There are a lot of darker spots. There are flares periodically. And all of that's rotating into and out of view and being created, being destroyed. So there's a lot going on. And just as a side note, a couple of days ago, that same observatory released a really cool video, a decade worth of observations of the sun. The video is over an hour long and it's really cool. So if you want to check it out, you can follow this QR code here or just search up NASA on YouTube. But back to the transit method. So in particular, something that can be really tricky is these darker spots that you probably saw in the video, which are called sunspots or star spots. And what makes it tricky is that these spots happen to be sometimes about the same size as the planets that we're trying to detect. And as the sun or the star rotates, those spots are rotating into or out of view. So it's hard to know if, when you're observing, if you see a dip in brightness, is that really caused by a planet passing in front of the star and blocking out some of the light? Or is it instead caused by one of these star spots rotating into view and then rotating out of view again? If they're about the same size, it can be tricky to tell. And then the last kind of main difficulty, not just with the transit method, but with every method we use to discover exoplanets, is that stars are just really far apart. So this is showing our sun with our closest neighbor, which is Proxima Centauri, which is 4.2 light years away from us. And that might not sound like very much, but 4.2 light years is 40 trillion kilometers. And that's the closest star to us, right? So when you think about the stars that the Kepler Space Telescope was looking at or other telescopes have looked at, on average, they're much further. Kepler, in particular, was looking at stars that were 600 to 3,000 light years away. And that's so far that I don't even know how to say that number in kilometers. So they're really far, which means they're pretty faint when we're observing them. And to make it worse, space is not empty, right? There's a lot of gas and dust and other things between us and those stars. And all of that can affect the light as it's traveling towards us and towards our telescopes. So it's not kind of the ideal picture that I showed before. Instead, I kind of like to think of it as detecting an exoplanet traveling around a star is kind of like trying to detect a speck of dust passing in front of the light from your cell phone from across Canada. So put that way, it sounds really difficult. And then the last method I wanted to talk about is direct imaging. I think sometimes when I tell people that I study exoplanets, we're going to talk about imaging exoplanets, people imagine we're going to see something like this. And it's not surprising because you see images like this all the time in university press releases or in the media, on TV, things like that. So this is, I think, what people think we might be able to see with direct imaging of exoplanets. But really, when we image an exoplanet, when we actually look at it directly rather than inferring its presence, we're going to see something a bit more like this, what's shown on the right. So this is an example where someone took a real photograph of the Earth and reduced the resolution of that photograph to the resolution that we might expect when we're actually taking a photograph of an exoplanet. So this doesn't look super exciting, I think, to see it like that. But in reality, I think it is really exciting. These kind of observations, to actually see an exoplanet ourselves with our own eyes, with observations, rather than inferring its presence around a star, it takes a lot of work to be able to do that. And for that reason, we haven't detected a lot of exoplanets with this method. But I think in the future, with upcoming extremely large telescopes that are being built, we will hopefully be able to do this for more exoplanets. So this specifically is an observation of the HR 8799 system, which was observed with direct imaging. And you can see here a couple things. So first of all, to actually be able to image an exoplanet directly, you really have to be able to block out the light from the star in the center, just because stars are so much brighter than the planets that are orbiting them. And if we don't have a way to kind of block out that starlight, that light's just going to overwhelm a lot of the planets. Sometimes I've heard the analogy of trying to look at a firefly next to a spotlight. The other thing that's really incredible about this and just shows how difficult this technique is, if you look on the bottom left, there's a counter showing how long this was observed for. So this was about 7 years of observations to observe these planets just moving a tiny bit in their orbit. So the first two methods I talked about, the transit method and the radial velocity method, they're kind of biased, I guess, towards detecting exoplanets that are really, really big and really close in to their host stars. Just because in the case of the radial velocity method, the bigger a planet is, the bigger of a wobble it's going to cause. In the case of the transit method, the bigger a planet is, the more light it will block out. And in the direct imaging case, we're also biased towards large planets, but planets that are further out in this case, because they're further away from the host stars. And so it's easier to detect them because the light from the host stars isn't interfering as much. So that's what you can see here. These planets are so far out that it takes years to observe them moving just a tiny bit in their orbits because their orbits are just so large. So those kind of three methods, the transit, the radial velocity method, and direct imaging, are three of the kind of most successful methods, I would say, for detecting exoplanets. And I think when you describe them and describe all the challenges that come with them, it makes it sound like it can be difficult to find exoplanets, and you might wonder how we could ever possibly get around all these challenges and actually find any exoplanets. But like I said at the beginning, we have found lots. We found over 4,000 now. And like I also mentioned, a lot of these are totally different from the planets in our own solar system. So this image here is showing in the center is our own solar system, shown with dashed lines. And the sizes of the planets are not to scale, but the sizes of the orbits are to scale. So we're just seeing our inner solar system here now. And the solid lines are showing the orbits of other planetary systems we've discovered. And the colors represent the temperature of those planets, and then the sizes of the planets are roughly to scale. So what we're seeing here, like I mentioned, is with these methods, we detect a lot of really big planets, much bigger than the planets in our own solar system, and a lot of planets that are really, really close in to their host stars. So I'll just let that play. This specific video is showing systems that were detected by the Kepler telescope. It's not entirely up to date, so there are some we've detected since this video, but this is showing a lot of them. So these are all systems that have been detected using the transit method. And that's kind of what I'll focus on for the rest of the talk, because my own research uses the transit method. So I'll just let that play. Okay, so now we know of thousands of exoplanets, right? We've discovered over 4,000 exoplanets, and we're pretty good at finding exoplanets by now. But the question that I'm really interested in is, what do we actually know about these exoplanets? Because with these methods that we use to discover them, we only learn so much about the planets themselves. So with the transit method and the radial velocity method, we can kind of learn a bit about how big the planet might be, or how far away it is from its host star in its orbit, so how long it takes to orbit around. But aside from that, we really don't learn too much just from detecting them. And what I'm interested in is learning more about the planets themselves and what they might actually be like on the surface. So how do we do that? My own research focuses on exoplanet atmospheres, and I use atmospheres to kind of try to learn more about what the planets might be like themselves. And the reason for this is because when you learn about what's present in an atmosphere, so what gases, what molecules, what atoms, it can kind of tell you about what conditions might be like on the surface of that planet, maybe, or maybe even in the interior of the planet. So for example, in our own atmosphere, you might know some of the molecules we have there, like we have water in our atmosphere. And so if you see that on an exoplanet, you might think, okay, maybe there could be liquid water on that exoplanet's surface. But how do we actually learn about exoplanet atmospheres? So to understand that, there are a couple key facts about light that you have to understand. So the first is that different types of gas absorb different colors of light. So in this example here, say I have a kind of greenish gas in the middle, and I'm shining all these different colors of light through the gas. So most of the colors of light will just pass through the gas totally unaffected, as if the gas is not there. But in this specific example, this greenish gas is absorbing this blue light and the green light. It doesn't absorb any of the other colors, just these two very specific colors of light. So I kind of like to think of this like a gumball machine. So with a gumball machine, you can only put in a quarter, right? You can't put in a toonie and then hope to get change afterwards. It just won't fit. You can only put in a quarter. So with gas, it's kind of a similar thing. Each different type of gas has a very unique set of colors of light that it will absorb. And you can't, say, shine purple light through this gas and have some of it absorbed and some of it pass through. The purple light, if I shine purple light through it, it's just going to pass through unaffected. But the green light in this case will be absorbed by the gas and it won't be able to pass through. And this is the same for every type of gas. They all have different colors that they'll absorb. The other kind of key fact is that stars emit light of every color. So while you might look at a star and maybe it looks kind of yellowish or kind of reddish, the reason for that is just because that star is emitting mostly that color of light. But really that star is emitting every other color of light as well, including some types of light that we can't see with our own eyes past the visible spectrum of light. So every star emits every type of light. So you can imagine then if we were to put this greenish gas in front of a star, which is emitting every color of light, again, the gas is going to absorb the blue light and the green light from the star, but all the rest of the light is just going to pass through unaffected. So like I said before, usually when you look at a star just with your naked eyes, you see kind of one color, and that's really a mix of all the colors that are being emitted from that star. But say that we break up the light, so with something like a prism, and that's kind of how the telescope and instruments that I use actually work. Like a prism, they break up all the light so that you can look at individual colors of light. So now say we're looking at a star that has an exoplanet orbiting around it, and that exoplanet has an atmosphere, which is made up of gas. And we're using something like a prism to look just at the orange light from this star. So in this example, the light that's directly behind the planet will be blocked because the planet is solid and the light can't travel through the solid body of the planet. But the light that's passing through the atmosphere will be unaffected because the atmosphere is made up of this very specific gas that doesn't absorb this orange light. But now if we were to look at just the green light that's being emitted by the star, not only is the light behind the planet going to be blocked by the solid body of the planet, but the light that's behind the atmosphere will be blocked as well. So in this case, there's more light being blocked than in the previous case where some light could travel through the atmosphere unaffected. And if you kind of compare these two side by side, again, when you're just looking at this orange light, only the solid body of the planet is blocking out light. But when you look at green light from the star, the solid body plus the atmosphere, the gas atmosphere, is blocking out light. And if you think back to the transit method, really what's happening here is that when you look in green light, there's more light being blocked, right? So if you have a transit light curve like we showed before, it's going to be a deeper dip because more light is being blocked when we look in green light as opposed to in this orange light. And so that's really how we can use the transit method. We take advantage of the transit method to learn about exoplanet atmospheres. So this video here is going to show on the top just the same kind of thing we saw before with the transit method and a planet passing in front. And then in the middle three, we're seeing if we just look at red light, just green light, and just blue light from that star. So what we can see here is that when we're looking at red light, the gas is not absorbing any light. The light is just passing through the atmosphere of the planet, and so the dip in brightness is shallow. But when we look at the green and the blue, those colors are absorbed by the atmosphere of the planet. And there's a deeper dip because more light is being blocked. And so from this, we can say, okay, we know that this atmosphere must be made up of a gas that absorbs green light and blue light, but not red light. So when I talked about the method, I think it sounds somewhat simple. And if you're looking for just a single gas, it can be simple. So this is the example of sodium gas, and this is actually the colors of light that sodium absorbs. So sodium specifically absorbs yellow light at these two very specific wavelengths, which are shown by these black bars here. But in reality, it can be a lot more complicated. So this is showing all the different colors of light that are absorbed by our sun. And you can see here there are a lot of black bars representing light that's being absorbed. And this is just the sun and what's in the atmosphere of the sun. So you can imagine if there was a planet there as well, it's going to absorb even more light, and it gets complicated. But we can use this method to learn about exoplanet atmospheres. So there are a couple other ways that we can take advantage of the transit method to learn more about exoplanets. So this is the research of other students. So this is a graduate student at Columbia University, Moya, and she uses the transit method to learn more about what the shape of a planet might be like. So in this example, we're seeing a planet that has a mountain, and that's changing the shape of the planet, and we see a deeper dip in the light curve. And so you can use kind of the shape of the light curve to tell you about the shape of the planet. So if you want to learn more about her research, you can follow that QR code here. Excuse me. This is another way we can take advantage of the transit method is to learn more about moons that are orbiting around exoplanets. So this is another graduate student from Columbia, Alex Tichy, and he studies how we can use light curves to learn about moons or exomoons around other planets. So in this example, we see the same kind of light curve that we saw before, but now we have a moon that's orbiting around the planet. And in the fourth panel here, you can see there's another dip caused by the moon passing in front of the star. So there was also, this was from a couple days ago, not too far away in London, Ontario, a group of astronomers from Western University also used this method to detect 6 potential new exomoons. And then one other example is we can use the transit method to literally measure the weather forecast on other worlds. So this is Diana Powell, who's a graduate student at UC Santa Cruz. And she showed recently that with the upcoming James Webb Space Telescope, excuse me, we could use the transit method to measure differences in cloud coverage on exoplanets. So she can measure, on the left-hand side, we're showing uniform cloud coverage all the way around the exoplanet. On the right-hand side, we have a case where the cloud coverage is just on one side of the planet. And she showed that the light curves are actually slightly different, but you can see in the bottom. And so with the transit method, we could learn more about, where clouds are on planets and really learn more about what the planets are like and what their weather is like. So with all this, we can discover exoplanets. We do a pretty good job at it. We can start to learn about what they might be like. So what have we actually found so far? So first, I just want to talk about the types of exoplanets we found. So this is our solar system, not really to scale, but roughly to scale in terms of the orbits. And then this is the kind of system that we first found when we started finding exoplanets, which is what we call a hot Jupiter system. So this is a system where we have a very large kind of Jupiter-sized planet, very close in to the host star. And these are, this is totally different from what we have in our own solar system, right? I think when people first discovered exoplanets, or they first set out to discover exoplanets, they thought that everything would look more or less like our solar system, with smaller planets in the inside and then bigger planets on the outside. But instead, we found a lot of these hot Jupiters, which are these systems with really massive planets really close in. And in fact, they're so close in that 1 year on these hot Jupiter exoplanets lasts only a few Earth days. So it takes them only a few days to orbit around their host star. And the reason for this, it's not because these systems are particularly common in the galaxy. Instead, it's because these are the easiest systems to detect with both the radial velocity method and the transit method. And I sort of talked about this before. It's mainly just because in the case of the radial velocity method, a really big close-in planet will cause a larger wobble in the host star. And so you're going to see a bigger red shift and blue shift in that light. It's easier to detect. In the case of the transit method, a bigger close-in planet will block more light from the host star. And so that dip in brightness will be bigger. And so again, it's easier to detect. So we found a lot of these. And these are just a couple examples that I wanted to talk about of specific systems that we found. So this is an exoplanet called WASP-76b. This is one of these hot Jupiter planets. So it's super close in to its host star. And a year on this planet only takes a few days. And a really cool discovery that was made sometime last year is that this planet actually rains iron. And the reason for this is because the planet is so hot that iron can actually start to evaporate, and it exists as a gas in the atmosphere. But this planet is also tidally locked, which is the case for a lot of hot Jupiters. And what that means is that the same side of the planet always faces the star. It's the same as what's going on in our moon. So the same side of the moon always faces the Earth. In this case, the same side of the planet always faces the star. And so on the hot day side that's always facing the star, you have iron in the atmosphere as a gas. But once winds blow that iron around to the dark night side of the planet, it will actually condense out and literally rain from the sky. So this is just an example of a planet that's, totally different from anything we have in our own solar system. Another one of my favorite planets is Kelt 9b, which again is one of these massive hot Jupiters. And in fact, this planet is hotter than some stars. So the day side of this planet that's facing the star can be up to 7,500 degrees Celsius. And for reference, our own sun, the surface of the sun is less than about 6,000 degrees Celsius. So this is an extremely hot planet, much hotter than any of the planets in our own solar system. And again, it has a really extreme atmosphere too. So there are heavy metals that have evaporated and exist as gases in the atmosphere. For this planet, 55 Cancri E, it's again a really hot exoplanet, but it's not a hot Jupiter this time. It's what's called the super-Earth. So this is a planet that kind of exists. It's a bit bigger than the Earth, a bit smaller than Neptune. It exists kind of in between. And this particular planet I'm studying right now in my own research, on the left is a kind of travel poster from NASA advertising this planet. And it says, "Skies sparkle above an ocean of lava." So what we think is that this planet, really the entire surface is molten rock, lava. And the planet itself probably has a lot of carbon, and the atmosphere literally probably has diamonds in it. So right now in my own research, I'm trying to detect an atmosphere and learn more about what might be there. It's definitely totally different from our own solar system, but I haven't detected anything yet. And then lastly, I wanted to talk about this planet K2-18b. This again is another super Earth or mini Neptune. So it's a planet that's kind of a couple times bigger than Earth, a couple times smaller than Neptune. And it's not as close in as the other examples I showed. It's a little further out. But it's really unique because in our own solar system, we don't have this type of planet, right? We don't have anything that's between the size of Earth and Neptune. We kind of have our smaller planets and our bigger planets. But it turns out these kind of in-between planets are really common. They're probably the most common type of planet that we found so far in the galaxy. This particular planet, you may have heard the name before because it was in the news a lot towards the end of last year. A team of astronomers used the kind of methods I talked about to find water vapor in the atmosphere. And so we got all of these kind of headlines here. Mini Neptune could possibly support life. Super Earth could have right conditions for life. Rainy exoplanet could be ripe for life. Water found on potentially life-friendly alien planet. So obviously the media went really wild about this. People were super excited. And in fact, I wrote an article about this too. And the headline that I didn't choose myself, but was assigned for me was biggest step yet towards finding life in space. So this is funny because this kind of happens a lot, I think, with media coverage of exoplanets. People are really interested in finding, life in space or another planet like Earth. This particular planet really isn't, I don't think is really habitable at all or anything close to, life in space. It's much bigger than the Earth. It has a lot higher pressure on the surface. And, a lot of people talk about, there's water, there's probably life there because there's water. But really this discovery was just water vapor in the atmosphere. They didn't necessarily find water on the surface. So while it is still really interesting, I don't think it's quite what people made it out to be. And that it kind of brings me to an interesting point that I want to finish off with, which is this idea of Earth 2.0. Because I think a lot of the time when I tell people I study exoplanets or I study astronomy, they always ask me, is there life in the universe? Are you searching for life or for another Earth or things like that? And I think it's interesting because a lot of the exoplanets we found are nowhere near Earth 2.0, right? They're totally different from the planets in our solar system, even more different from the Earth. And something else I find kind of funny, I guess, as an astronomer is I see signs like this a lot, saying there is no planet B. And it's funny to me, and maybe you'll have picked up on it too if you're paying attention to the names of those planets I was talking about, that the convention we use to name exoplanets is that we name them after the star they're orbiting around, and then give them a letter based on which the planet was found. So K218b is orbiting around the star K218, and it's the first planet, so it's planet B. So really, there are planet Bs. There are right now more than 3,000 planet Bs that we found in our solar system, or in our galaxy, sorry. But the funny thing is that while we have found a lot of planets, they're really totally different from the Earth, and there is really no Earth 2.0. And even if we were to find one day, they're so far away from us that thinking that we could actually go there and find life there or live there ourselves really isn't realistic right now. So for me, I think that's kind of one of the best parts about studying exoplanets and learning more about all these different really extreme systems that are out there. Because the more I learn about all these really extreme planetary systems, the more it kind of reminds me and makes me appreciate how unique our own Earth really is. So thank you so much. And I'm happy to take any questions.
Thank you so much, Ms. Deibert. We are going to head now to our coordinator, Celia Du, for questions from our YouTube audience. Celia?
Thank you. And thank you so much, Emily. That was really wonderful. So we do have a few questions. One of them is noting that the radial velocity method was used by Dr. Bolton, who has a strong connection to the DDO, and he discovered Cygnus X1.
Yes.
And that yes, and that method is also used for exoplanets. Do you have any comments on that?
No, yeah, that's a great point. Yeah, there's definitely, I'd say in the whole field of exoplanets, there's a lot of Canadian connections. So yeah, it's nice to hear that.
Yeah. Where can you look up exoplanet numbers?
Oh, okay. Yeah. So NASA has if you just search Exoplanet Archive, they have a website there where they've got it's completely up to date. That's why I said, I checked these numbers yesterday. So they update it all the time, and you can look up all the different planets we've discovered. It's really easy to search through them. So it's NASA Exoplanet Archive.
Great, thank you. And then a more personal question, how did you get interested in this, in exoplanets, and even the methods that you're using?
Yeah, that's a good question. I had a bit of a weird path into astronomy, I guess. I wasn't, I was interested in astronomy as a kid, I guess, but I never really saw it as something that I would pursue any further than an interest. So when I started university, I was actually going to get a degree in English. But we have to, at the University of Toronto, take a science credit. So I took a science credit that was an Astronomy 101 course, and it was taught by Mike Reed at the University of Toronto and Chris Matzner. And I just found it super inspiring. And I remember them talking a bit. The course wasn't about exoplanets, but they mentioned a bit about it because it was kind of in the news a lot at that time. And so, I just decided I hadn't done physics or anything in high school, but I decided, oh, this is really inspiring and really cool. So I want to switch into this and continue pursuing it. So I never really imagined that I would end up doing a PhD in this field, but I eventually got there.
Nice. I feel like that's very hopeful for a lot of young, aspiring students, right? So thank you for that. What do you think is going to happen in the next 5 to 10 years?
Oh, that's a good question. Yeah. So there's, like I mentioned briefly, there's the TESS telescope, which has launched last year. I believe it launched. So that's also using the transit method to find new exoplanets. And that's already been super successful, and they've made a ton of discoveries. That one is interesting because they're looking more at stars that are closer to the Earth, whereas Kepler was looking at sun-like stars, which were a bit further away. So probably we'll see a lot more detections from that. A bit further in the future, we will have bigger telescopes on the ground that we can probably use to more better directly image exoplanets. But that's more than 5 years, I would say, in the future.
Exciting. What do you do to mitigate the Earth's atmosphere from affecting your results?
Yeah, that is a really good question. That's really like the bane of my existence, I guess. So it's, obviously the Earth's atmosphere also absorbs light. So without going into too much detail, basically what I do is the exoplanet is moving really quickly in its orbit. And the Earth's atmosphere is more or less, it's not moving as quickly relative to the planet. So we can kind of track how the light is changing as a speed of how quickly the planet is moving. And we can kind of disentangle it from the Earth's atmosphere that way. So that's what I do in my own research, because I use telescopes on the ground. A lot of people just use telescopes in space so that you don't have to worry about that.
Right, nice. Is direct imaging biased to face on?
Oh, yeah. So yes, yeah. It would be easier to detect, like if you're looking at from above, like I showed before. And then the other methods are more biased towards it has to be edge on. The transit method really has to be more or less edge on. Radial velocity doesn't have to be entirely edge on, but it can't be face on because the star has to be moving towards you or away from you a little bit at least.
Right. And so why have you chosen the transit method as opposed to others? Other than it's useful, is there any other reason or preference for it?
I think for me, it was just when I kind of got into astronomy was right around when Kepler was making a lot of discoveries. So it was, that was kind of the big thing at the time. And so it was kind of what got me interested in exoplanets.
Cool. How do you distinguish a star spot versus a planet?
Yeah, that's a good question. So I kind of alluded to that as being a difficulty. So when we are using the transit method, we have to observe and see the planet pass in front a couple times to actually confirm that the planet is there. The star spots they don't last forever. So if you observe the star long enough and it is a star spot, eventually the star spot's going to fade away and it won't be there anymore. Whereas the planet is going to keep orbiting. So if you observe and see the planet orbit or see this dip in brightness, say 5 times, then okay, that's probably a planet at this point and not a star spot, which would have faded away.
Okay, that's really good to know. And this next question is about the spectroscopy part. Mm-hmm. What are the resolution factors for very small planets?
So I would say with my own research, I'm not even looking at super small planets yet because I think our telescopes just aren't quite there to be able to do this method that I talked about with the exoplanet atmospheres. So the telescopes I'm using have resolutions of 80,000 to 100,000, which is a really high resolution. But even with that, I'm really only looking at hot Jupiters, which are really big, or super Earths, which again are somewhat big relative to an Earth-sized planet. So I think to actually use these kind of methods that I talked about for looking at atmospheres on smaller planets, we really have to wait until the next generation of telescopes and instruments.
Okay. Well, that's going to be exciting then. So why are there so many discoveries in 2016 compared to what TESS is finding in 2019 and 2020?
Yeah, so I think if we look at that graph again in like a year or so, you'll see a big spike there. But TESS, well, it did launch last year. It took a while to actually get started. So it has discovered a lot so far, and I'm sure it will keep discovering more. But we're only partway through the year so far, so I think we have to wait, and we'll see more eventually. But yeah, the big spikes that you see in 2016, and I think there was one in 2014 maybe, are just because that's when we were getting data from Kepler and analyzing it and making most of those discoveries from Kepler.
Right. Is it that we need other techniques to find Earth-like planets? Are we biased to other types of planets right now?
Yeah, so we're definitely biased in our techniques to larger planets. So I don't think we necessarily need different techniques to find Earth-like planets. More just that we need more sensitive telescopes and instruments, and more time to observe. Mm-hmm. So to find planets that are, like the size of Earth, we can do if they're close in. For planets that are the size of Earth and also have a year as long as us, like an orbital period the same as the Earth, that's tricky, right? Because we'd have to observe for more than a year to be able to see it transit twice.
Right. Good to know as well. Can you speak about the selection effects among different detection methods?
Yeah, so again, I think it's there are a couple of different ones. So definitely we're going to be mostly seeing these big planets just because they're so easy, and these big close-in ones because they're so easy and they transit so often that we can detect them quickly. Those are actually, so these hot Jupiter systems, like I said, at the beginning especially, we mostly detected these, but they're actually not very common in the galaxy. So I think the latest number I heard was something like maybe 0.5% are hot Jupiters. So it's really not very many hot Jupiter systems that exist, but we're more biased to finding those. And then again, there's a selection effect for systems with the transit method for systems that are edge on. So if a system is face on to us and the planet doesn't transit relative to our point of view, then we can't detect it, of course.
Right, yeah. What might be the coldest exoplanet, and what is it like?
That's a good question. So off the top of my head, I don't know what's the coldest one we've discovered so far. There are definitely some we've discovered that are in really, really long orbits. So like much longer orbits than even the furthest away planets in our own solar system. So those ones would be really, really cold. And, a year on them would be really long. You'd receive very little sunlight. There's also what's known as rogue planets. So these are planets that aren't orbiting around any star for whatever reason. Maybe they've been kicked out of their system through gravitational interactions. And so those are probably even colder because they don't have a star to give them any light. So I think it's hard to say. We probably couldn't live on something like that. So it's hard to say what it would be like to live there. But yeah, those would probably be the coldest, or rogue planets.
Oh, rogue planets. Never heard of them before, but cool. So it seems like there are more and more discoveries. Are you using crowd support, crowd research, like community science? Or?
Yeah, that's it. So I personally don't, but there are a lot of great community science projects for exoplanets specifically. So perhaps people have heard of Zooniverse, which is kind of a platform for gathering these community science projects together. And they had a program with Kepler and now have one with TESS, where you can look at these kind of light curves like I showed, and you decide, okay, does this look like a planet or not? And you flag it for them. And there have actually been like publications in scientific journals from these platforms, from the Zooniverse platforms, where we have discovered planets that way.
That's amazing. Yeah, I've heard of Zooniverse. I think it's pretty fun to use.
Yeah.
So it's good to know. How will James Webb Telescope change planet hunting?
Yeah, so James Webb is an upcoming telescope, although it's been upcoming for a while, so hopefully it will launch soon. And it will just be a much better suited for a lot of these techniques I talked about for studying exoplanets. And it will be in outer space. So there was a question before about how the Earth's atmosphere affects things, so this won't be affected by the Earth's atmosphere because it's in outer space. And a lot of its kind of primary mission will be looking at exoplanets and learning more about their atmospheres. So that will definitely, I think, change. It'll teach us a lot. It will teach us a lot that we can't currently learn with the telescopes we have. So hopefully that launches soon and we'll get to learn more.
Amazing. I think this may be our last question. The RASC DDO team have had a number of conversations about diversity and inclusion in astronomy and improving that in recent weeks. So what has your experience been as a woman in astronomy? And do you have any suggestions about how we can maybe facilitate access to STEM fields, particularly astronomy for women and maybe perhaps people of color, if you can speak on that?
Mm-hmm. Yeah, that's a great question. So I think I've been lucky. The department I work in is it's very welcoming and inclusive, and especially to women in science, we have a really good balance, especially among the graduate students, but now also among faculty. Like in recent years, they've hired a lot more faculty who are women, and so for me personally, like I find it does help to have kind of these role models who look like me and are in the same groups or demographics as me to look up to in the field. And so I'm lucky that I've had that within my own department, to some extent within my field too, like exoplanet science. There are a lot of really great women in the field who I can look up to. I think, in terms of like improving that, I think just having access to programs, especially free programs for younger people who might be from groups that are not typically represented in the field is really important. So that's why I think it's great to have things like this where people can join for free, especially from home, from wherever they are, and learn more about what's going on. The Dunlap Institute, where I'm a student as well, also has kind of a lot of programs like this that really is welcoming to everyone. And so I think that sort of thing is great to get people interested and get people involved in the field.
Awesome. Thank you so much. Over to Denise.
On behalf of the Royal Astronomical Society of Canada, Toronto Centre, and the RASC DDO Committee, I'd like to thank Emily Deibert for introducing us to some incredible worlds beyond our solar system. Thanks also to our technical support team, Andrew Reed, Betty Reed, Blake Nancaro, Ward Legros, and Ennio Cellucci, and to our coordinator, Celia Du, for organizing this event and for fielding questions from the YouTube chat. A special thank you to all of our viewers for joining us this evening and for your questions. This talk is part of a series of lecture nights at the David Dunlap Observatory, offered through the partnership of the Royal Astronomical Society of Canada Toronto Centre and the City of Richmond Hill. For a complete schedule of RASC events, please visit us online at rascto.ca. Our next lecture night at the DDO online will feature Rachel Ward-Maxwell, who will talk about inspirational astronomical phenomena. That will be July 11th at 7:30 p.m. We'll see you back here for the live stream of that event. Until then, wishing you all clear skies.